The last thing we're going to do is talk about piecewise functions, and we're just going to do that using an example, 2.3.5 in your textbook. And it's going to be to solve dy dx plus y is equal to f of x, where y of 0 is equal to 0, and f is given in a special way. F of x is equal to 1 for 0 less than or equal to x less than or equal to 1, and 0 for x greater than 1. So sort of to solve this, we have a new thing where f is piecewise defined. Actually, I should write that right here just in case you don't have that word for it. And that's something that we're going to have to worry about later. But for now, we're just going to sort of start with this is a first order equation. We're going to solve it the way we solve all of our first order linear equations. So we get it into the standard form, dy dx plus py is equal to f. It's already like that. And so we can see that p of x is equal to 1 times y. So the integral of p of x dx is equal to integral of 1 dx is x, and e to the integral of p of x dx is just e to the x. So our integrating factor is e to the x, and we're going to have, I decided that I want to change that to the differential equation can be written as d over dx e to the x times y is equal to e to the x times f. And so we would normally solve that by saying, okay, I integrate d dx of e to the x y dx. And I set that equal to the integral of e to the x f of x dx. So I get e to the x y is equal to, I don't know what goes right there. And this is the part where the piecewise function f matters. So sort of, if we imagine that x falls between 0 and 1, then the integral of e to the x times f of x dx, actually, let's just leave that question mark there. The integral of e to the x f of x dx is just the integral of e to the x times 1 dx. So that's just e to the x plus some constant c. If x is bigger than 1, then the integral of e to the x f dx would be sort of, you integrate from 0 to 1, e to the x times 1 dx, plus you integrate from 1 to x of e to the x times 0 dx. Sort of, we could imagine this, let's draw a quick picture of f. So we've got f, we've got x, and at 1, it kind of changes from being up here at 1 to down here at 0. Actually, let me use a different color for that. Okay, so this area under the curve right here is, if you wanted to find the area under the curve, so you're kind of evaluating your integral at this point, you would collect all this area up to here and then nothing after 1 is kind of the idea. And so let me just draw that box of green stuff is the integral from 0 to 1 e to the x, and then this part that's just like, oh no, I didn't actually change colors. This part that's just kind of flat and there's nothing there. That's just 0. For the first integral, what's happening is you're kind of like right here at some unknown x, and so you had collected that version. Um, so maybe I can try to draw that kind of like this so that you can see in your notes kind of what's happening in that picture. Okay, and so the second integral is just going to be the integral from 0 to 1 e to the x dx plus 0. So that's just e to the 1 minus e to the 0. So e to the 1 minus 1. And so let's go ahead and kind of plug this in. So we have, continued. Really just having trouble with that word today. Continued. Okay. So our last statement had been e to the x times y is equal to whatever came out of the integral. So if 0 is less than or equal to x is less than or equal to 1, then e to the x times y is equal to e to the x plus c. So when we solve for y, we get y is equal to 1 plus c e to the minus x. And if y of 0, I think was given as 0, then 0 is equal to 1 plus c e to the minus 0. So that's just 1 plus c, which means that c is equal to minus 1, and the solution is y is equal to 1 minus e to the minus x. If x is greater than 1, we have to think about that different integral now, that longer piece we had. So we still had e to the x times y, but we said that was equal to this piecewise integral broken up into its two parts, which just gave us e to the 1 minus 1, which is going to tell us that y is equal to e to the minus x times e to the 1 minus 1. And then what's going to happen is we therefore have y of x is defined in two different ways. It's either going to be 1 minus e to the minus x for 0 less than or equal to x less than or equal to 1. It's going to be e to the minus x times e to the 1 minus 1 for x greater than 1. That's the whole solution to this initial value problem. The solution with piecewise input f is to have piecewise y. In general, you can kind of remember that rule of thumb. And then sort of an important consideration for piecewise problems is kind of what happens at the break. And for us, that was x equals 1. So our function f changed values at x equals 1. Our solution y changes values at x equals 1. And so we're kind of curious what happens right there. So y is equal to either 1 minus e to the minus x or e to the minus x times e to the 1 minus 1. And if you plug in 1 for either, what you'll get is 1 minus e to the minus 1 on top, or e to the minus 1 times e to the 1 minus 1, which is just 1 minus e to the minus 1 when you multiply it through. So the solution is continuous when crossing x equals 1. Now, the reason I brought this up is because If you got unknown constants in your second f integrals, this is how you would solve for them. That's really important. It will come up and you'll be confused about what to do. So here, my integral went away. It was 0. But if I had held on to that integral, I would have had an unknown constant. Sort of like if it was e to the x times 2, I would have 2 e to the x plus c. And so if I had that unknown constant, you would just set y of 1, or whatever your breakpoint is, equal to y of 1. To solve for unknown constants. After you've plugged in your initial condition. So you'll get a chance to actually practice with that yourself, but just kind of make a note for when that happens. This is how you do it.